Thank you, Professor. Okay. Yeah, it's working. So, I would like to thank the organizer and thank the chairman and thank the organizer for inviting me to present some of my recent work, which is a part of my PhD student, Pragati Firwani. And it's a pleasure to be back here in JNU. I did my PhD from here almost 18 years back, and then it's always good to be here. And I would like to thank the organizer again for organizing this very good conference, which has been organized in a very well uh, efficient manner. So, since there has been a lot of talks about quantum materials and quantum spin liquid in previous 2-3 days, so there is a kind of lot of stage has been set, and for the benefit of a student, I will take uh, some benefit of that stage. And since I belong to this UGC Consortium for Scientific Research, so many people may not be knowing about my institute. So I will, in the outline, I will first talk about who are we. I'll take 5 minutes from the chairman, and experts may please excuse me for 5 minutes. And I'll talk about what are we and who are we and what we do offer, and then I'll come to the topic of my talk. So basically, this UGC-DAE Consortium for Scientific Research, it's a basically collaboration between UGC and Department of Atomic Energy, which was established in 1989 as a Inter-University Center for DAE facility. So we were basically mandated to promote, coordinate, and encourage university researchers to use the state-of-art DAE research facility. So DAE has many state-of-the-art facility which cannot be replicated in the university level and at the many times. So it is always better that if DAE has spent a lot of money, so ideally speaking, DAE people should be directly approached, but somehow the system is a bit opaque. So somehow we are working as an interface between university users and DAE. And most important aspect is that it is at no cost to users. So basically nowadays when we hear that many facilities are on chargeable basis, so this is not on charge basis. And in 2003, our mandate was expanded further to establish our own state-of-the-art, so-called state-of-the-art facilities, and we were renamed as UGC-DAE Consortium for Scientific Research. So currently we have 4 centers. So Mumbai Center basically is inside VARC, so takes care of neutron-related facilities. And Indore Center looks into synchrotron facilities. So these 2 facilities, you must have heard many talks that neutron scattering and synchrotron are very useful technique to characterize your samples, and these are available in India. And then cyclotron based research is being taken care of by the Kolkata Center, and Kalpakkam Center is basically looking into the multidisciplinary research, and new node has come up in IOP Bhubaneswar. So with this concept has given a new direction and meaning to collaborative research schemes in India. So if I can tell you that we have almost 1,000 users all over India in last, we can say more than 5-6 years. This is 2020, almost 3-year-old data. So the number must have increased further. And Mumbai Center basically looks into neutron scattering facilities, which comes under National Facility for Neutron Beam Research. And we coordinate utilization of these facilities by research community. So since there is a limitation of time, so I'll not go into each and every facility, but using neutron, you can characterize your sample using elastic scattering as well as inelastic scattering. Inelastic scattering is INS, which has been discussed in quite detail in this conference, and elastic scattering is basically neutron deflection. So there are different beamlines. So these beamlines takes care of all kinds of spectrum using neutron. And if you want to access these facility in a one-time mode or long-term collaboration, so you can write to us for any time, whatever suits you. And then more than, I would say that almost in last 20 or 25 years or so, more than 300 long-term CRS proposal has been accepted or has been completed in fact. So CRS is a long-term CRS proposal which is committed 3-year beam time. And then this is our facility which is built up by our institute at, this is Dhruva reactor. So this is a neutron diffractometer. I'll talk about in detail, but just for the sake of completeness, I will just say a few words about neutrons. So neutron, you know, this is spin half particles, and due to spin half particle and its interaction with the matter, in case of you, if you want to see your compound through the lenses of X-ray, you will see the element like this, because there is a Z factor involved in the intensity. So in the limitation is that if you have neighboring element, you cannot distinguish between these two neighboring element. In case of neutron, the intensity is a constituent of a scattering amplitude factor, and which basically you can see the elements like this. So it means you can identify neighboring element also. So that is the benefit of neutron. Moreover, there is a no form factor dependence in case of neutron. So if you look into the X-ray, as you go towards higher to star value, you will see the peak intensity decreases. But in case of neutron, at least for structural part, there is no decrease in the intensity peak. You will see in the example in next few slides. And since it's a spin half particle, so it carries a movement. So this movement is a, you can consider as a tiny magnet. If these tiny magnets interact with your magnetic movement present in your sample, so you can identify the magnetic structures also. So this magnetic structure can be AFM, FM. In the easiest case, it can be spiral or in different format. So that is the benefit of neutron. And this is our beamline. Our beamline basically has a this silicon doubly focusing monochromator. So neutron beam is coming like this, and after monochromatizing it is focusing on the sample. So it's a kind of focusing crystal diffractometer. So then the flux is one order higher, and we have having an option of different planes. So you can have different wavelengths in the angular range of 6 degree to 123 degree, and resolution is around of the order of 0.3 degree. So and we have option of temperature variation from 1.6 to 300 Kelvin with the help of magnet, and then we can go up to 7 Tesla. And in regular CCR make system, we can go up to 2.7 Kelvin to 300 Kelvin, and this is in air. So this is the actual picture of neutron beam. So as you understand, neutron beam is bit wider. We cannot make it point-like. If we make it point-like, then flux will reduce further, so there will be no good signal to noise ratio. So that is the reason we require little more sample. Typically 3 gram sample is required, but these samples are totally recoverable. We can return the sample back to you, and there is no any problem with the sample. So if you want to have more detail about other facilities in the BRC or other NFNBR facility, you can just look into NFNBR. You can just put into Google into NFNBR, and then you can get more information. So coming back to some other in-house facility, we have, in addition to neutron diffraction, we have other facilities like sample synthesis and sample characterization and PPMS. All these facilities are available to all the users. You just have to write a proposal and then submit to us, and then we can take care of this facility. Since there is a no cost involved, so definitely there is a long queue, but we can definitely take care. So this was from the perspective of student. So now coming back to my actual talk. So as I mentioned, it is already discussed that when about frustration in the magnetism, that when most magnetic materials are cooled to nearly absolute zero, so the ground state can be ferromagnetic or antiferromagnetic depending upon the orientation of spin. And then in 1973, Professor Anderson mentioned that there can be another class of material or which may have constantly fluctuating spins, and it does not freeze even at down to 0 Kelvin or so. So which are called quantum spin liquid system. So basically, as if you have seen the talk that listened the talk previously, so in triangular spin lattice compound, so this is kind of frustration spin which doesn't know how to and where to orient to fulfill the minimum energy condition. And because of this, this quantum spin liquids are are being explored at different compounds, and different compounds. So one of the compound which I am going to show is will be here. So basically, in typical quantum spin liquid, you will see spins are not freezing; they are fluctuating randomly, and then that can be useful for many quantum related technologies. So it can be quantum computing and quantum communication and quantum sensing. So how to identify the quantum spin liquid, that has been also discussed at quite length. So it may be repeating slide, but it is better to have a repetition kind of, you can get much better idea that since there is no perfect technique which can say, based on which we can say that particular sample is a quantum spin liquid or not. So we can have NMR or EC susceptibility, or μSR and neutron scattering are more not easily available, but EC susceptibility up to 2 Kelvin or magnetization up to 2 Kelvin are easily available. So you can definitely characterize your sample using these regular characterization, and then you have to look for millikelvin kind of facility which can talk about whether your compound is in spin liquid state or not. So usually when we carry out the if there is a magnetic movement present in a sample, or if it is magnetically ordering, then you will have the lambda like peak. But in case of QSL kind of compound, you will not see the any lambda like peak. This is the one, sorry, this is the one signature. And then if you can do the μSR or NMR kind of experiment, this will be more comprehensive experiment to show that whether this is QSL behavior or not. And then neutron scattering, of course, will be very useful. And I'm talking about scattering as well as diffraction. So diffraction is also very useful in terms of, if you can do the diffraction, you can identify whether magnetic structure is there or not. So coming back to this topic of this talk. So basically QSL or quantum spin liquids are being explored in various series of compounds. So one such compound, I mean, was a very common lattice is a Kagome lattice, which is consisting of two-dimensional corner sharing triangles, and it exhibits various exotic magnetic phenomena due to this structure. And among Kagome lattice, there are many compounds which has been explored or are being explored. So for the I mean, these are very common compounds which has been reported enormously. But here in this, for the present talk, I will be talking about the compound which is derivative of this pyrochlore structure. So pyrochlore is a very commonly studied, or maybe not common, but it has been very precisely studied, which shows spin ice behavior. But in pyrochlore structure, we can have a 2D Kagome lattice layer. So if we look into the pyrochlore structure, so it is like this along the 111 plane. So if we can replace certain atom or certain element in such a way that it can form a kind of 2D layers. So 2D layers, so these are Kagome layers. So Kagome layers, so if we look, modify the formula of A2B2O7 from A2B2O47, we can write it as A4B4O14. And in this context, we can choose certain element at A site and B site partially, so that it can form a 2D layers, 2D Kagome layers, and then this can be a potential candidate for quantum spin liquid. So, or if we look into more precisely, so then you can see this is a pyrochlore structure. So this is in different orientation, this is in different orientation. So by replacing these non-magnetic atoms, we can have layers like this, so which are in the form of Kagome, as we can see here. So in this series, there is a if we replace A and B atom in such a way that we have A atom which is 2dimensional, or sorry, divalent non-magnetic atom, and place Sb3, and then it will be rarer 3. So using this combination, we can have a compound which having different divalent atom, and rare earth can be different rare earth. So initially the first compound was reported in by Kava's group in Princeton University in 2016. So this was a series which was proposed in 2016, in which many compounds are being explored, and some compound has shown the regular magnetic behavior, but some compound has shown the signature of QSL. So we are exploring, we have taken the compound HO3SB3 Zn2O14. So this compound was synthesized in single phase. Most of the compound, though when you have a kind of oxygen are there, so sometimes it is not easy to make in the single phase, but we have made this compound in single phase, and this is the X-ray diffraction refinement. So we have used the regular rhombohedral structure R3 bar M 166 space group. So if you look into the refinement of X-ray, it looks okay, but if you look carefully in this peak, so then by zooming this over here, you can see in the refinement, this is the calculated data, but this is observed data. So observed data with the regular position of HO and RE and SB at different locations. So we could not able to refine it. But if we introduce the disorder, means some HO is at Zn site and some Zn is at HO site, so then you can refine this data. So this shows that in this particular compound there is a site mixing or disorder, we can say, is there. So that is from the X-ray part. But since, as I mentioned earlier, that if you go towards higher 2 theta value, so the intensity decreases because of form factor dependence. So we wanted to see what is happening in neutron. So neutron, as this is already shown. So neutron, you can see this 100% peak, and then even up to 120 or 115 or so, the peak intensity is not very less as compared to this peak. So the refinement looks good over here because of you are refining these small peaks. So it's refining a small peak. Yeah.
What is the fraction of the site mixing?
Site mixing, I'll tell you. This is typically 20% we have observed.
That's
so
large.
Yeah, that's quite large. So I'll show you the data, in fact. So then, so here the refinement may not look like very precise, but if we look into the goodness of fitting parameter, these are reasonably okay. And because of SB, slightly the scattering is an issue, but still we can say as compared to X-ray, the refinement is much better. And as you have talked about the site mixing, so this is the site mixing obtained from neutron part. Basically, we have looked into neutron part. So this HO at 9E, HO and Zn, so there is disorder of the order of 20%. But here in case of HO and Zn at 3A site, we have seen roughly 50-50. So this is quite large, and but we have carried out refinement at a very different manner. As I showed you one example of X-ray, so there is a clear-cut signature. So, but in case of neutron, if I show you the data, further data at, so these are the crystallographic parameters that the cell parameter are of the order of 7.339 and 17. So this is slightly larger. So, but I'll talk about this in later part of this. And then this is the structure which we have determined from the analysis of our data, and then we can see that there are HO3 and Zn layers are there, and in which the disorder or site mixing is there. So after characterizing the data structurally, we have again analyzed the bulk magnetization. So bulk magnetization, if you see, this is 100 off-state data. Yeah. So ZFC, FC are retracing each other, so there is no sign of any magnetic ordering. And then this is isothermal magnetization at 5K and 300K. So isothermal at 300K, it is kind of paramagnetic, and this is also showing non-saturating behavior. And there is no signature of any loop. So how much time I have, sir?
You have 5 minutes.
Oh, okay.
No, 7 minutes.
Okay. So then we, in order to carry out whether can we see the ordering at different measuring fields, so we have measured the data, ZFC, FC data in different measuring field, and we could see that there is no effect of any measuring field. In fact, if we plot it together, then chi inverse versus T. So chi inverse, in which basically M divided by H is considered, so effect of field is considered. So it is perfectly matching. So from magnetization, we could not see any signature of magnetic ordering. And for generally in this kind of compound, we see that if there is a possibility of crystal field effect. So we have fitted the chi basically the theta CW and H mu effective has been calculated. So theta CW in the range of 2 to 30 Kelvin, we have seen this is around minus 1.86. And since this is not ordering, so we can say the Tn is very close to 0. So definitely there will be a lot of if we consider theta P over Tn, so then it will be quite high. So this is frustrated system. And then we have again carried out a specific heat to look into for the search of magnetic ordering. So here also we have seen there is no ordering, and even if we see this data in close proximity, there is almost linear. So again, when we did the neutron diffraction and up to 2 Kelvin, so we have not seen any signature, neither there is a structural transition nor there is a magnetic transition again this portion site mixing, we have seen that site mixing remains constant at the lowest temperature up to 2 Kelvin. So this encourages us to look into more characterization in terms of millikelvin format. So we have carried out AC susceptibility in millikelvin. This was carried out at ISIS, and then we could see there is slight frequency dependence has been observed. So whether this is showing some glassy nature or not, that we are trying to understand in terms of previous report. But slight glassy nature, can it be termed as magnetic or not, that we have to identify. So that is one part, and then again we have looked into the specific heat. So specific heat at under magnetic field in low temperature millikelvin range. So we could see that as we increase the temperature, as we increase the field, at around 2 Kelvin, the field intensity suppresses the magnetic field. So this looks to be Schottky anomaly. And then in C by T versus T, we could see that as we increase the field, there is a negative dependence, temperature dependence. So this could be there could be possibly indicating emergence of quantum critical region in this system around low T temperature. And then this is the neutron diffraction which we have carried out at the 30 millikelvin. So you can see up to 2 Kelvin data I have shown. This is 1.7 and 3 millikelvin, 30 millikelvin. So this we have carried out in the lambda value of 2.44 to look into the large Q range. So sometimes it may happen that if there is a large cell, so your magnetic ordering may come at the lower Q range. So in order to nullify the effect or identify, so we have done neutron diffraction. This was done at Arnstow. So we could see that this is totally retracing 1.7 to 30 millikelvin. This is totally retracing. So there is no signature of magnetic ordering through neutron diffraction. And we have carried out INS experiment to understand the excitation in this compound. So we have seen the signature of CEF, but we are still in process of understanding this data more carefully. As I mentioned, this is ongoing work, so we are exploring many options. So with this, I come to my summary of this talk, that this compound has been made in single phase, and then XRD neutron diffraction shows there is a site mixing in the compound, and magnetic ordering is not observed down to 40 millikelvin and even 30 millikelvin. I would say that in case of neutron diffraction, we have not seen any ordering. So the data suggests there is this possible QSL-like behavior present in the sample, and then further analysis of INS and CEF is in process. And MUSR experiment, which is a very inconclusive proof. So we are trying to explore if we can get the MUSR beam time. So this is the only thing. And apart from that, we are also trying to look into other samples in this series, and hopefully some of the series will show similar kind of behavior. So that is, with this, thank you very much, and I would like to acknowledge collaborators from different institutes. So with this, thank you. If any questions, then.
Yeah, thank you, Professor Kaushik, for the nice talk. The house is open for questions.
So, because the voice temperature itself is of order 1 Kelvin.
Yeah, minus 1.86 or so. Yeah.
So, I mean, there will be no order above that. So, there's no surprise there.
Yeah.
And because of your large disorder, at lower temperatures, you do indeed see a broad anomalies in AC susceptibility as well as C capacity. So, would it just be disorder effect?
Yeah, possibly, because we have looked into, though this is perfectly ordered as reported in the previous literature, but we have seen disorder in HO and ZN sites.
Right.
So that could be the possible reason for this kind of problem in or observation in the AC susceptibility. And in fact, if we can analyze this CEF.
I mean, so, the point is that because of the large disorder,
yeah.
I mean, maybe the Karome,
yeah.
they are not isolated, they are actually forming some 3D connection.
Yeah, so that definitely. So we are looking forward for some theoretical calculation if we can have. That will be very supportive to this. From experiment, we can just speculate, but if we can get some theoretical support, that will be quite assertive in this.
Okay. You can also try to make better samples, maybe, I don't know.
Samples we have actually tried, and we could see that maybe we can try another time that there is no disorder, but disorder we have made the sample 2 or 3 times.
Is the holmium and zinc sizes the same or similar, or why do they?
Holmium is bigger, yeah, much bigger, but still we have seen, because from X-ray we could see that the particular smaller peak was not fitting. So we were, I mean, our story is quite relying upon that. This is not, because otherwise if we can skip that peak, we can say this is not a disorder compound, but we are focusing on very minute information, so that's why we are saying that there is a disorder involved.
No, your refinement gives 50%
yeah,
zinc.
Exactly.
And zinc are the layers which are separating the carbonate.
Yeah,
so
exactly.
50% of those are holmium, then it's not
possibly
carbonate.
there is a possibility that some connections are making it to make it kind of glassy behavior.
Thanks.
Yeah.
Nice talk, Kaushik. So one point I'm not able to understand, because you go to structure actually.
Okay.
So here your antimony and zinc are non-magnetic, right? 5 plus and 2 plus.
Yeah.
So now if you have this, because you're A2B2O7, you are doubling this, right? So then your cagomel lattice is formed by holmium, right? And the lattice is not fully occupied by holmium. The holmium associated with another non-magnetic compound.
Yeah, holmium is
because the
basically
cagomel is itself not a magnetic. It's a some kind of diluted.
Yeah.
Right?
So actually we have made some other compounds also in which holmium is not there, Nd is there, in which we have also we have not
because
seen.
3 here.
Yeah. So we have made another compound which is basically Nd in place of holmium, in which we have not seen the disorder.
Is it possible to prepare real earth 4 Sb2 Zn2? Then your all this cagomel lattice will be occupied by magnet.
So my point is that in apart from HO we have made few other compounds in which there is no ordering is there, but that also showing similar kind of behavior. So I have not shown here in this presentation, but yeah, as you said that HO layer may be having some connotation regarding this magnetic behavior which we have seen in the magnetic.
His point is that even in an ideal structure where there is no mixing, the kagome is diluted with zinc.
Okay.
So if you make holmium 4 Sb3 zinc, something like that, then all of the kagomes are magnetic, and then you can say that it is a kagome lattice.
Okay.
Otherwise, it is a diluted.
Right. So that can be thought of definitely.
Thank you, sir, for the nice talk. Sir, just one question regarding the INS data. Sir, sometimes you get some phonon peaks in the INS data. So, have you grown any non-rare earth analog?
Yeah. We have grown actually in place of HO. We have placed La, so that is non-rare earth. I mean, in fact, non-magnetic.
Yes.
So that in specific heat we have subtracted that data from 2 Kelvin to 300 Kelvin as well as low temperature, millikelvin range also.
So in INS as well.
Yeah.
Okay. Thank you, sir.
One is that side. Maybe you can speak. Sorry? So this crystal electric field data we have not analyzed yet. So this is, we are in process of analyzing it through INS.
Yes, sir. This is a 2-level CF system or 3-level? I want
2 level or 3 level means.
In the energy levels, it is.
Could you go to the
Means so Schottky name it is also.
the inelastic data?
Okay. Inelastic actually we are still in form of analyzing because we have just got the data. So I would not say we have completely understood it. So yeah. So we have carried out at the 750 and 150 Kelvin. So which shows that.
So there is a distribution.
Yeah. So this.
Broad.
Yeah.
Nice talk, sir. I just had a very naive question. Like you see a small angle, like small angle peaks, and you're completing this. This is a sign of disorder. But isn't it the case that the ordering gives us small low angle peaks?
No, in case of X-ray, there is no peak coming because of any magnetic ordering. So that is coming only from structure part.
Yes.
Yeah, so X-ray will not give you the magnetic peak or very small peak which we are considering as a structure.
No, I'm asking about the disorder part from X-ray. So you could not fit the data
using the regular HO and ZN at different at their particular Wyckoff position.
So I'm curious, are you sure that it's not from some minor impurity phase?
No. See, as I showed you that if we introduce this anti-site disorder, so this is, if you look into this, so if we introduce, I mean, if there is no disorder is introduced, then these are the calculated peak and this is observed data. And if we introduce a disorder which I just showed, that we can nicely fit the peak. So this blue is the fitted data and black is the observed data. So I mean, though if you look into the whole angular range, so it looks a very small peak, but we have carried out this experiment several times, X-ray, and we have made this compound at least 2 or 3 times. So still we have got this kind of behavior. So this is very consistent, at least from our side.
Okay.
Yeah.